24,791 miles per hour. That is the fastest humans have ever travelled. 3 astronauts aboard Apollo 10 achieved this record in 1969, hurtling around the moon at velocities no human has matched since. At that blistering speed, you could cross the United States in 6 minutes. You could circle Earth in 1 hour. You could reach the moon in 10 hours. But reaching Jupiter at that speed would still require 2 years of continuous travel. And Alpha Centauri, the star system closest to our Sun, over 115,000 years, the astronauts who departed would be dust long before their great-great-grandchildren's great-great-grandchildren glimpsed the destination. We dream of starships and warp drives. Physics dreams of keeping us exactly where we are. If you want to understand why the cosmos keeps us trapped on this tiny rock and what it would actually take to break free, consider hitting that like button and subscribing. Your support helps bring these cosmic journeys to more curious minds. Now, get yourself nice and comfortable. Let's begin. Look up on a clear winter night and find the brightest point of light that does not twinkle. That steady glow is Jupiter, a world so massive it could swallow 1,300 Earths and still have room for more. Ancient Romans named it after the king of their gods. Modern astronomers know it as the solar system's dominant planet, a failed star that nearly ignited into a second sun but fell just short of the mass required for nuclear fusion. Jupiter appears close. Your eyes can see it without any optical assistance. Amateur telescopes reveal its cloud bands and the 4 largest moons that Galileo discovered over 4 centuries ago. Spacecraft have photographed its storms in stunning detail. The Great Red Spot, a hurricane larger than Earth that has raged for at least 350 years, seems almost familiar from countless images printed in textbooks and displayed on documentary screens. This familiarity breeds a dangerous illusion. Jupiter feels like a place we could visit, a destination within humanity's reach. After all, we have sent numerous probes to the gas giant. Juno currently orbits Jupiter, sending back breathtaking images of swirling cloud formations and polar auroras that dwarf anything on Earth. Pioneer 10 became the first spacecraft to fly through the asteroid belt and past Jupiter in 1973. Voyager 1 and 2 followed in 1979. Galileo orbited the giant planet for 8 years, beginning in 1995. We have touched Jupiter with our machines. We have photographed its moons in exquisite detail. We have dropped a probe into its atmosphere and recorded data as it plunged through cloud layers before being crushed by pressure equivalent to 100 Earth atmospheres. Surely sending humans cannot be much harder than sending robots. But confirmed measurements reveal a truth that should shatter any casual assumptions about reaching Jupiter. The average distance between Earth and Jupiter measures 484 million miles. This number appears in textbooks and websites, yet its true meaning escapes human intuition. Our evolved brains, designed for navigating African savannas and tracking prey across distances measured in miles, cannot process distances measured in hundreds of millions of miles. The number 484 million sounds large but abstract. Your mind cannot visualize it any more than it can visualize what $1 billion looks like stacked in cash. These numbers exist beyond the scale of human experience. They become mathematical symbols rather than physical realities we can comprehend. Let me translate this cosmic gap into terms your mind can grasp. If you could drive a car at highway speeds toward Jupiter, maintaining 65 miles per hour continuously without stopping for fuel, food, or sleep, the journey would require over 850 years. You would need to start driving before the Norman conquest of England to arrive today. William the Conqueror would have been preparing his invasion fleet as you departed Earth's surface. Every empire that rose and fell during the medieval period, every plague that swept across continents, every war fought over territory and religion, every scientific revolution that transformed human understanding, the Industrial Revolution would transform civilization. The Renaissance would begin and end. Commercial aircraft travel faster than cars. A Boeing 747 cruises at roughly 570 miles per hour. At that speed, the flight to Jupiter would take approximately 97 years. Your great-great-grandchildren might see the destination you departed toward as an infant. The Wright brothers achieved powered flight in 1903. If they had immediately launched toward Jupiter at jet airliner speeds, their aircraft would still not have arrived today. Even our fastest rockets move at speeds that render Jupiter frustratingly distant. The New Horizons spacecraft, which flew past Pluto in 2015, travelled at speeds exceeding 36,000 miles per hour relative to the Sun. This is faster than any bullet ever fired, faster than any jet aircraft ever flown, faster than the escape velocity needed to leave Earth's gravitational grip forever. At that velocity, reaching Jupiter's average distance would require approximately 560 days of continuous travel. Nearly 2 years of racing through the cosmic void at speeds that make terrestrial transportation look stationary. And New Horizons represents one of the fastest launches in human history, but New Horizons benefited from a gravity assist that accelerated it to exceptional speeds. The spacecraft was flung past Jupiter itself in 2007, using the giant planet's immense gravity as a cosmic slingshot. Most Jupiter-bound missions travel far slower, because they need to slow down enough to enter orbit rather than flying past at 36,000 miles per hour. Juno, the spacecraft currently studying Jupiter, launched in August 2011 and did not enter orbit around the gas giant until July 2016. 5 years of travel to reach a world visible to the naked eye. 5 years of crossing empty space while Earth completed 5 orbits around the Sun. Children born on launch day entered kindergarten before Juno arrived at its destination. The Galileo spacecraft took even longer. Launched in October 1989, it did not arrive at Jupiter until December 1995. 6 years of voyage through the cosmic void, despite being aimed at a destination ancient humans could see every night. The Berlin Wall fell during Galileo's journey. The Soviet Union collapsed. The World Wide Web was invented. All while a single spacecraft drifted through interplanetary darkness toward a planet our ancestors worshipped as a god. These transit times create immediate problems for human exploration. An astronaut departing Earth today for Jupiter would spend years in a spacecraft before reaching the destination. The return journey would require additional years. A round trip to Jupiter using current propulsion technology would consume a decade of human life minimum, possibly longer depending on mission parameters and orbital mechanics. Consider what a decade means for a human being. A child becomes an adolescent becomes a young adult. Careers are built and sometimes abandoned. Relationships form and dissolve. Parents age and sometimes die. The world changes in ways no one can predict. All of this would occur while astronauts drifted through space in a metal container, smaller than most apartments. But time represents only the first barrier. The energy requirements for Jupiter missions reveal why human exploration remains pure fantasy with any technology we can currently envision. Consider what happens when a spacecraft travels from Earth to Jupiter. It must first escape Earth's gravitational well, requiring velocities exceeding 25,000 miles per hour. Our planet does not release objects easily. Gravity clings to everything on Earth's surface with a force that humans struggled for millennia to overcome. Rockets must carry enough fuel to achieve velocities that break this gravitational bond. Then the spacecraft must travel through interplanetary space for years, while life support systems maintain astronaut survival. Every breath requires oxygen that must be stored or generated. Every exhale produces carbon dioxide that must be scrubbed from the air. Body heat must be managed in an environment where external temperatures fluctuate between scorching sunlight and absolute cold shadow. Finally, the spacecraft must slow down enough to enter Jupiter's orbit rather than simply flying past the planet. This deceleration phase represents perhaps the most challenging aspect of the journey. A spacecraft arriving at Jupiter carries tremendous kinetic energy from years of acceleration by the Sun's gravity. Shedding that energy requires fuel expenditure comparable to the initial launch. Each of these phases demands enormous energy expenditures. The fundamental problem is energy density. Chemical fuels store limited energy per kilogram of mass. The bonds holding molecules together simply cannot contain enough energy to accelerate spacecraft to the velocities interplanetary travel demands. This limitation is not an engineering problem, awaiting a clever solution. It is a ceiling imposed by the laws of chemistry themselves, a barrier that no rocket design can circumvent regardless of funding or ingenuity. A spacecraft capable of carrying humans to Jupiter would need to transport life support systems, radiation shielding, food supplies, water recycling equipment, medical facilities, and numerous redundant systems to ensure crew survival during the multi-year journey. Conservative estimates suggest that a crewed Jupiter mission using chemical propulsion would require spacecraft with initial masses measured in thousands of tons. Most of this mass would be fuel that burns away during the first hours of the mission, leaving only a tiny fraction to actually reach the destination. Launching such a behemoth from Earth's surface would be essentially impossible with current technology. The vehicle would need to be assembled in orbit from hundreds of separate launches, each costing hundreds of millions of dollars, years of construction in space, using techniques we have barely begun to develop, just to build a ship capable of attempting the voyage. The total mission cost would exceed $1 trillion, likely by significant margins. This sum exceeds the entire gross domestic product of most nations. No government has ever committed such resources to a single endeavor. No private organization possesses such wealth. But suppose unlimited budgets existed. Suppose humanity decided to send astronauts to Jupiter regardless of expense. Suppose a global civilization committed its full economic output to this single goal. The journey would still face insurmountable challenges that money cannot solve. The Jupiter system itself presents dangers that would threaten any human visitors. The giant planet generates the most powerful magnetic field of any planet in our solar system, approximately 20,000 times stronger than Earth's magnetic field. This immense magnetosphere traps charged particles from the solar wind and from volcanic eruptions on the moon Io, creating radiation belts of terrifying intensity. These radiation belts make Earth's Van Allen belts look like gentle breezes compared to hurricanes. The trapped particles carry energies that would destroy electronics and devastate biological tissue. A human standing unprotected in Jupiter's inner radiation belts would receive a lethal radiation dose within minutes. Even heavily shielded spacecraft suffer damage from this bombardment. The Galileo spacecraft experienced significant electronic degradation during its 8-year mission, despite being designed with radiation hardening. Mission planners deliberately crashed Galileo into Jupiter, partly because radiation damage had compromised its systems. Juno uses a titanium vault weighing approximately 400 pounds to protect its most sensitive electronics, and even this protection only allows brief passes through the inner magnetosphere before retreating to safer distances. Human explorers would face far greater exposure challenges than robotic spacecraft. Humans cannot be rebooted when their systems glitch. They cannot have damaged components replaced with spares. The biological damage from Jupiter's radiation environment would accumulate in ways that no engineering solution can fully address. Europa, perhaps the most intriguing of Jupiter's moons, orbits squarely within these deadly radiation belts. This ice-covered world is thought to harbour a liquid water ocean beneath its frozen surface, making it one of the most promising locations in the solar system for finding extraterrestrial life. Scientists dream of sending submarines to explore Europa's hidden seas, but any mission to Europa's surface would need to contend with radiation doses approximately 540 rem per day. For comparison, the annual radiation exposure limit for nuclear workers on Earth is 5 rem. A single day on Europa's surface would expose astronauts to over 100 times the maximum annual dose allowed for radiation workers. Extended exploration would be suicide. Io, the innermost of the 4 Galilean moons, presents different but equally lethal challenges. This tortured world is the most volcanically active body in the solar system, with hundreds of active volcanoes continuously erupting sulfur and silicate magma across its surface. Massive volcanic plumes rise hundreds of kilometers above the surface, feeding a torus of plasma that orbits Jupiter and contributes to the deadly radiation environment. Landing on Io would mean setting down on a world of constant seismic activity, where the ground itself rises and falls by up to 100 meters due to tidal flexing from Jupiter's immense gravity. Rivers of molten sulfur flow across plains of sulfur dioxide frost. Lakes of liquid lava glow in the darkness. Even without the radiation, Io would be one of the most hostile environments imaginable for human exploration. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It possesses its own magnetic field, the only moon known to have one, which provides some protection against Jupiter's radiation. But Ganymede lies over 665,000 miles from Jupiter, adding significant distance to any mission profile, and its surface temperature averages negative 171 degrees Celsius, cold enough to make steel brittle. Callisto, the outermost Galilean moon, offers the most benign radiation environment among Jupiter's large moons because it orbits beyond the worst of the radiation belts. Some mission planners have proposed Callisto as a potential base for human operations in the Jupiter system. But Callisto lies over 1 million miles from Jupiter itself, meaning missions to the inner moons would still face the radiation gauntlet. The diversity of challenges across Jupiter's moon system illustrates the compound difficulties facing human exploration. Each destination presents unique hazards. Radiation levels vary dramatically depending on orbital position. Surface conditions range from volcanic hellscapes to frozen ice worlds. No single mission architecture could address all these challenges simultaneously. Communication delays add another layer of complexity to Jupiter missions. At Jupiter's distance, radio signals take between 33 and 53 minutes to reach Earth, depending on orbital positions. This communication lag eliminates real-time conversation with mission control. Astronauts would send messages and wait over an hour for responses. A simple question would require more than an hour for an answer. During emergencies, astronauts would need to solve problems independently, with no possibility of immediate guidance from Earth-based experts. Imagine facing a life-threatening equipment failure, while knowing that the nearest help is over half an hour away by radio. Imagine making split-second decisions while knowing that advice from experts would arrive only after the crisis resolved itself one way or another. The Apollo missions benefited from communication delays of only about 1¼ seconds. Mission control could respond to astronaut questions almost immediately. Flight controllers could monitor telemetry in real time and provide guidance during critical maneuvers. This close coordination between ground and crew was essential to mission success. At Jupiter, no such coordination would be possible. Every procedure would need to be planned in advance. Every contingency would need to be anticipated. The astronauts would need to function as a self-contained team, capable of handling any situation without external assistance. Food supplies present another critical problem that scales dramatically with mission duration. This basic metabolic requirement cannot be reduced through engineering. Bodies burn energy, regardless of circumstances. A crew of 6 on a 10-year round-trip Jupiter mission would need to consume over 40 million calories of food. This represents tens of thousands of pounds of provisions that must be launched from Earth or grown during the voyage. Every ounce of food adds to spacecraft mass, driving fuel requirements higher. Growing food in space remains experimental and limited. Current systems aboard the International Space Station can produce limited quantities of leafy greens, mostly as psychological benefits for crew, rather than significant nutritional contribution. Producing enough calories to sustain astronaut health through multi-year missions would require agricultural systems far beyond current capabilities. Medical emergencies represent perhaps the most sobering consideration for long-duration missions. If an astronaut develops appendicitis during a Jupiter mission, there is no possibility of emergency return to Earth. The spacecraft cannot simply turn around. Orbital mechanics does not permit such flexibility. The journey must continue regardless of medical complications. Appendicitis is just one example. Heart attacks, strokes, traumatic injuries, infections, kidney stones, dental emergencies, and countless other medical conditions could strike during a decade-long mission. The spacecraft would need to carry surgical facilities, diagnostic equipment, pharmaceutical supplies, and someone trained to use all of it. Consider the contrast with current human spaceflight. Astronauts on the International Space Station can return to Earth within hours if serious medical emergencies develop. Soyuz capsules remain docked specifically for emergency evacuation. Landing sites around the world stand ready to receive returning crews. Hospitals near landing zones prepare for any medical contingency. This safety net disappears completely beyond lunar distance. Once a spacecraft departs for Jupiter, its crew is committed. No rescue mission could reach them in time. No emergency evacuation is possible. Whatever happens during the voyage, the crew must handle alone with whatever resources they brought from Earth. Solar power becomes increasingly problematic at Jupiter's distance from the Sun. The intensity of sunlight decreases with the square of the distance from the Sun. At Jupiter's orbit, solar intensity drops to approximately 4% of the value available at Earth's orbit. Solar panels that would generate kilowatts near Earth produce only tens of watts at Jupiter. The Juno spacecraft uses 3 massive solar arrays, each nearly 30 feet long, to generate approximately 500 watts at Jupiter. This represents a dramatic decrease from the 14 kilowatts those same panels would produce at Earth's distance. Powering life support systems for a human crew would require solar arrays measured in acres, adding enormous mass and complexity. Nuclear power systems offer an alternative, using the decay of radioactive isotopes or controlled fission reactions to generate electricity independent of sunlight. But nuclear systems add their own mass, complexity, and safety concerns. Radioisotope thermoelectric generators like those powering the Voyager spacecraft produce only hundreds of watts each. Fission reactors capable of powering human habitats have never been operated in space. The thermal environment near Jupiter presents additional engineering challenges unlike anything encountered near Earth. The giant planet radiates approximately 1.6 times more heat than it receives from the Sun, a consequence of ongoing gravitational contraction and helium precipitation in its deep interior. Spacecraft in Jupiter's vicinity must manage thermal conditions that include both this radiated heat and the cold of deep space. Jupiter's cloud tops register approximately -145 degrees Celsius, while its interior reaches temperatures exceeding 30,000 degrees. The moons experience temperature variations between day and night, between areas in sunlight and areas in Jupiter's shadow, that would stress any human habitat. Managing these thermal extremes requires sophisticated climate control systems that must operate flawlessly for years. All of these challenges compound each other in ways that make crewed Jupiter missions practically impossible with foreseeable technology. Each problem solved creates new problems that demand their own solutions. The spacecraft grows heavier, requiring more fuel, which requires a larger vehicle, which requires more life support capability, which requires more power, which requires more mass. This self-reinforcing cycle explains why no serious mission architecture for crewed Jupiter exploration exists in any space agency's actual planning documents. NASA studies human Mars missions because Mars appears barely achievable with revolutionary but conceivable technology development. No comparable studies examine human Jupiter missions because they are not feasible. The technology gaps are not small incremental advances waiting for engineering cleverness. They are fundamental barriers that may take centuries to overcome. The moons of Jupiter will likely remain the domain of robots for the foreseeable future. The Europa Clipper mission, scheduled to launch in the mid-2020s, We'll conduct detailed flybys of that intriguing moon without ever landing on its surface. Even robotic landers face severe challenges from the radiation environment, limiting mission durations to weeks rather than years. Dreams of swimming submarines beneath Europa's ice, of rovers exploring Ganymede's ancient surface, of astronauts watching Jupiter rise over volcanic Io, these visions belong to a future so distant that no one alive today will see their realization. The gap between our current capabilities and the requirements of Jupiter exploration spans centuries of technological development, assuming such development is even possible. Yet Jupiter represents a destination within our solar system. It orbits the same star that warms our planet. Light from the sun illuminates its clouds. When we look at Jupiter, we see reflected sunlight that departed the sun only 43 minutes earlier. In cosmic terms, Jupiter is right next door. If reaching this nearby neighbour seems impossible, consider what lies beyond our solar system's edge. The stars visible in the night sky exist at distances that make Jupiter look like it is right across the street. The 484 million miles separating Earth from Jupiter would need to be multiplied by hundreds of millions to match interstellar scales. The nearest star system to our Sun is Alpha Centauri, a triple star system containing two Sun-like stars locked in mutual orbit, plus a smaller red dwarf called Proxima Centauri. Recent observations confirmed that Proxima hosts at least one rocky planet, roughly Earth-sized, orbiting within its habitable zone. This tantalizing discovery sparked renewed interest in interstellar travel. A potentially habitable world exists just over 4 light-years away. Science fiction has long imagined starships carrying humans to distant solar systems. Surely humanity could reach such a nearby destination, especially given the exponential growth of technology over recent centuries. The reality is far more sobering than any science fiction has dared to depict. The distance to Alpha Centauri makes Jupiter look like a stroll across a parking lot, and the challenges of crossing that interstellar gulf reveal that humanity may be permanently trapped within our solar system, gazing at stars we can never touch. But before we can understand why Alpha Centauri is unreachable, we must first grasp the true scale of the abyss between stars. That incomprehensible void is where our hopes for starflight go to die. The night sky appears filled with stars. From dark locations far from city lights, thousands of stellar pinpoints create the impression of cosmic abundance, a universe packed with accessible destinations waiting for human visitors. Ancient sailors navigated by these lights. Poets wrote verses about their beauty. Religions placed gods and afterlives among their glittering patterns. The stars seem close enough to touch on clear mountain nights, when the atmosphere barely interferes with their ancient light. This impression could not be more wrong. The night sky presents the most deceptive view in all of human experience. Those lights that appear clustered together are separated by chasms so vast that crossing them would require timescales exceeding the entire history of our species. What looks like a crowded celestial neighborhood is actually the loneliest expanse imaginable. Stars are separated by distances so vast that human language struggles to describe them. The numbers involved exceed the capacity of intuition shaped by evolution on a single small planet. When scientists discuss interstellar distances, they resort to metaphors and analogies because raw measurements lose all meaning. The numbers become strings of digits that convey mathematical relationships, but fail utterly to communicate physical reality. Alpha Centauri lies 4.37 light-years from our solar system. This statement appears in astronomy textbooks as a simple fact, yet it conceals a truth so staggering that most people who read it never grasp its implications. Light, travelling at 186,282 miles per second, requires over 4 years to cross this gap. The fastest speed possible in our universe, the ultimate cosmic limit that nothing can exceed, still demands years to reach our nearest stellar neighbour. Consider what light speed actually means. A beam of light can circle Earth's equator 7.5 times in a single second. Light crosses the distance from Earth to the Moon in about 1.3 seconds. The sun's light reaches Earth in approximately 8 minutes. Light travels so fast that for all practical purposes on Earth's surface, it appears instantaneous. Yet this inconceivable velocity still requires 4 years and 4 months to reach Alpha Centauri, the fastest thing in the universe. Moving at speeds our minds cannot truly comprehend, crawls across the interstellar void like a glacier advancing across a continent. If light itself takes years to make the journey, what hope exists for spacecraft moving at tiny fractions of that speed? Let me translate this distance into conventional units that might provide some foothold for understanding. Alpha Centauri's distance of 4.37 light-years converts to roughly 25.7 trillion miles. Written out fully, this number is 25,700 billion miles. This number appears in calculations and scientific papers, yet it conveys nothing to human experience. We have no frame of reference for trillion-mile distances. Our brains evolved to navigate terrestrial environments measured in miles, perhaps hundreds of miles for the most ambitious journeys our ancestors undertook. The longest migrations in human prehistory covered thousands of miles over generations. Trillions of miles exist beyond our cognitive architecture entirely. Consider some comparisons that might illuminate the scale of what we are discussing. If you could drive to Alpha Centauri at highway speeds of 65 miles per hour, the trip would take over 45 million years. You would need to start driving when dinosaurs still roamed Earth and continue without stopping for fuel, food, or rest, until long after human civilization had risen, flourished, and potentially fallen. 45 million years ago, the dinosaurs had already been extinct for 20 million years. Mammals were diversifying into the ecological niches left vacant by the Great Extinction. Early primates were just beginning their evolutionary journey toward humanity. No creature resembling a human being existed anywhere on Earth. If your ancestors had started driving toward Alpha Centauri at that moment, maintaining highway speed through every geological epoch, every ice age, every mass extinction, every evolutionary breakthrough, the car would not yet have arrived. The emergence of Homo sapiens, the development of language, the invention of agriculture, the rise and fall of every human civilization, all of recorded history and prehistory combined, would represent less than 1% of the journey duration. Commercial aircraft would reduce travel time only marginally in any meaningful sense. At 570 miles per hour, the journey would still require approximately 5.2 million years. The entire history of our species, from the first anatomically modern humans walking African savannas to the present day, represents less than 1/10 of this duration. Even our fastest spacecraft move at speeds utterly inadequate for interstellar travel. Voyager 1, currently the most distant human-made object, travels at approximately 38,000 miles per hour relative to the Sun. This velocity exceeds anything achievable by terrestrial transportation. It is faster than any bullet, faster than any jet aircraft, faster than the escape velocity needed to leave Earth's gravitational grip. At this impressive velocity, reaching Alpha Centauri would require over 77,000 years. This duration exceeds human comprehension in ways that demand careful consideration. 77,000 years represents roughly 3,000 human generations. Every generation that has lived since modern humans first appeared would need to pass again, and then once more. Consider what this means for any living crew aboard such a spacecraft. If Voyager 1 carried human passengers who departed today, the original astronauts would die within decades. Their children would be born in the void between stars, knowing nothing of Earth except stories passed down from parents who were themselves children at departure. These children would grow old and die during the voyage, passing the mission to their own offspring. Generation after generation would live and die aboard the spacecraft, each knowing nothing but the interior of a metal vessel drifting through absolute darkness. No crew member alive at departure would survive to see arrival. No crew member at arrival would have any direct connection to the world that launched the mission. Only the final generation, born after 77 millennia of travel, would glimpse the Alpha Centauri system with their own eyes. Approximately 3,000 human generations would pass during the journey. What language would these distant descendants speak? Human languages change dramatically over mere centuries. The English of 1,000 years ago is barely comprehensible to modern speakers. Over 77,000 years, language would evolve into forms unrecognizable to the original crew. The mission objectives recorded in departure documents would become as mysterious as undeciphered ancient scripts. Human civilization as we know it has existed for roughly 6,000 years, dating from the first cities in Mesopotamia to the present. The journey to our nearest stellar neighbor at current spacecraft speeds would take 13 times longer than all of recorded human history. Every dynasty that ever ruled, every religion that ever spread, every empire that ever rose and fell would fit within a small fraction of the voyage duration. But Voyager's speed represents what we can actually achieve with current technology. This is not a theoretical maximum, but an actual demonstrated capability. The Parker Solar Probe achieves speeds exceeding 430,000 miles per hour during its closest approaches to the Sun, the fastest human-made velocity ever achieved. At that remarkable velocity, Alpha Centauri would still require approximately 6,800 years to reach. The wheel had not been invented. Copper tools were just beginning to replace stone. If ancient humans at the dawn of metallurgy had launched a Parker Solar Probe speed spacecraft toward Alpha Centauri, that spacecraft would be arriving approximately now, after all of human recorded history had occurred during its transit. The void between stars that any interstellar spacecraft must cross is not merely empty space. It is a region so devoid of matter that it challenges comprehension. On Earth, even the best laboratory vacuums contain billions of molecules per cubic centimeter. The interstellar medium contains roughly 1 atom per cubic centimeter, 1,000,000 billion times emptier than any vacuum we can create. This emptiness extends for trillions of miles in every direction. No asteroids drift through this void. No planets orbit in the darkness between stars. No comets trace lazy ellipses through the interstellar deep. There is nothing but scattered hydrogen atoms, traces of helium, wisps of cosmic dust, and the endless radiation of distant stars. The psychological weight of crossing such emptiness would crush human spirits in ways we can barely imagine. For years or decades or centuries, travellers would see nothing outside their windows but unchanging star fields. The sun would dwindle from the giver of life to just another star, eventually becoming indistinguishable from the thousands of other points of light. Alpha Centauri would brighten so slowly that no human eye could detect the change from year to year. No rescue would be possible once a spacecraft departed the solar system. No supply ships could catch up with a vessel travelling at interstellar velocities. No communications could provide real-time guidance as the spacecraft moved beyond the solar system's edge. The travellers would be more isolated than any humans in history. Separated from their species by distances that light itself needs years to cross. The destination that awaits at the end of this impossible journey is not a single star, but a complex triple star system. Alpha Centauri consists of 3 stellar components, locked in an intricate gravitational dance that has continued for billions of years. Alpha Centauri A is the primary star, slightly larger and brighter than our Sun. If you stood on a planet at the same distance as Earth orbits the Sun, Alpha Centauri A would appear noticeably brighter and slightly more yellow-orange than our familiar day star. This star is approximately 5 billion years old, slightly older than our Sun, and has likely burned steadily for most of that time. Alpha Centauri B orbits in partnership with A, the 2 stars circling their common centre of mass in an elliptical path that takes approximately 79 years to complete. At their closest approach, the 2 stars come within 11 astronomical units of each other, roughly the distance from the Sun to Saturn. At their farthest, they separate to 36 astronomical units, beyond the orbit of Neptune. This binary dance creates a constantly shifting gravitational environment that would make stable planetary orbits difficult in certain regions. Planets orbiting too far from either star would be perturbed by the gravity of the companion star, their orbits destabilized over millions of years. Only planets orbiting close to either star, within a few astronomical units, could maintain stable paths over billions of years. Alpha Centauri b is smaller and cooler than its companion. It possesses approximately 90% of the Sun's mass, and shines at roughly half the Sun's luminosity. Its light appears more orange than our Sun's, the colour of a star slightly cooler than the yellow dwarf we orbit. Despite being smaller than A, Alpha Centauri b has attracted significant attention from planet hunters searching for potentially habitable worlds. The third member of the system, Proxima Centauri, is a tiny red dwarf star orbiting the central binary at an immense distance. Proxima lies approximately 13,000 astronomical units from Alpha Centauri A and B, over 400 times the distance from the Sun to Neptune. At this vast separation, Proxima takes approximately 500,000 years to complete a single orbit around the central pair. Proxima Centauri is a mere wisp of a star, containing only about 12% of the Sun's mass. It shines so dimly that despite being the closest star to our solar system, it cannot be seen with the naked eye. You need a telescope to detect this nearby cosmic neighbour. If the Sun were a bright searchlight, Proxima would be a birthday candle viewed from miles away. But this dim red dwarf has captured scientific attention, far exceeding its modest luminosity. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri within its habitable zone. This world, designated Proxima Centauri b, has a minimum mass approximately 1.3 times Earth's mass. It orbits its star at a distance of only 4.7 million miles, completing one orbit every 11.2 Earth days. This close orbit places Proxima b within the habitable zone of its cool parent star, the region where temperatures might allow liquid water to exist on a planet's surface. Because Proxima Centauri is so much cooler and dimmer than the Sun, its habitable zone lies much closer to the star than Earth's distance from the Sun. A planet needs to huddle close to a red dwarf to receive enough warmth for liquid water. The discovery of Proxima b electrified the scientific community and the general public alike. A potentially Earth-like world existed at the nearest star system to our own. If interstellar travel were ever possible, Proxima b represented the closest possible destination, a target that might be reached before more distant stars. But closer examination revealed sobering complications. Proxima Centauri is a flare star, a type of red dwarf that periodically releases tremendous bursts of radiation. These flares can increase the star's brightness by several times within minutes, bombarding any nearby planets with ultraviolet radiation and high-energy particles. In 2017, astronomers observed a superflare from Proxima Centauri that briefly made the star 68 times brighter than normal in certain wavelengths. Any unprotected life on Proxima b would have been bathed in sterilizing radiation. Such flares may occur frequently enough to strip away any atmosphere the planet might possess, leaving a barren rock exposed to the vacuum of space. Furthermore, Proxima b orbits so close to its star that it is almost certainly tidally locked, meaning one side permanently faces the star while the other side faces the eternal darkness of space. The day side would be perpetually illuminated by the red light of Proxima Centauri, while the night side would never see stellar light at all. Such a configuration creates extreme temperature differences between the two hemispheres. The day side might be scorchingly hot, while the night side freezes toward absolute zero. Only in a narrow twilight zone between day and night might temperatures permit liquid water. Whether such a restricted habitable band could support life remains unknown. Additional planets have been detected or suspected in the Alpha Centauri system. Proxima Centauri c, announced in 2020, appears to be a super-Earth or mini-Neptune orbiting much farther from the star, well outside the habitable zone. Evidence for planets around Alpha Centauri A and B remains tentative, with claimed detections later disputed or withdrawn. The uncertainty surrounding planets in this nearest star system illustrates how little we know even about our closest neighbours. Decades of observation have produced only tentative detections and disputed claims for the main binary stars. The dynamics of the binary orbit may have prevented planetary formation entirely, or may have ejected any planets that formed early in the system's history. Even if ideal planets exist in the Alpha Centauri system, reaching them remains functionally impossible. Nuclear pulse propulsion, the most powerful practical propulsion technology ever seriously designed, could theoretically achieve 3 to 5% of light speed. At 3% of light speed, approximately 20 million miles per hour, Alpha Centauri would still require well over a century to reach. Project Orion, the 1950s study that explored nuclear pulse propulsion, proposed using nuclear explosions behind a spacecraft to provide thrust. Each explosion would push against a massive plate, gradually accelerating the vessel to velocities impossible for chemical rockets. The concept was physically sound but practically impossible. Exploding nuclear bombs in Earth's atmosphere would create catastrophic radioactive fallout. The technology could only be assembled and operated in deep space, requiring industrial infrastructure in orbit that humanity has never developed. The cost would exceed the entire economic output of human civilization accumulated over many years. Even if nuclear pulse propulsion could somehow be achieved, the journey time of 140 years still spans multiple human generations. Astronauts who departed as young adults would die of old age decades before arrival. Any vessel attempting such a journey would need to sustain a viable human population for over a century. The minimum founding population to maintain genetic diversity across multiple generations is approximately 160 individuals. Larger populations of several thousand would provide greater margins against unexpected deaths and genetic bottlenecks. Sustaining such populations requires closed-loop life support systems that recycle all air, water, and nutrients with near-perfect efficiency for longer than any human technology has ever operated continuously. Every breath exhaled must be processed. Every drop of water consumed must be recovered. Every nutrient must cycle through the system indefinitely without loss. Space between stars is not truly empty, and what little matter exists becomes dangerous at the velocities required for practical interstellar travel. The interstellar medium contains approximately 1 hydrogen atom per cubic centimetre on average. This is fantastically empty by terrestrial standards, but becomes significant at relativistic speeds. A spacecraft travelling at 3% of light speed would impact interstellar hydrogen at approximately 20 million miles per hour. At these velocities, individual atoms carry significant kinetic energy. Billions of impacts per second would create a cumulative radiation effect at the spacecraft's bow, potentially harming any crew positioned near the leading surface. Cosmic dust presents an even greater danger. Interstellar space contains microscopic particles of rock, ice, and carbon, scattered throughout by stellar winds and supernova explosions. These particles range from individual molecules to grains the size of sand, invisible to any detection system at interstellar distances. A dust grain weighing 1 milligram, travelling at 3% of light speed relative to a spacecraft, carries kinetic energy, equivalent to approximately 10 kilograms of TNT. This tiny particle, invisible to the naked eye, would strike with explosive force sufficient to breach a spacecraft hull. A vessel crossing 4 light-years would encounter many such particles during its century-long voyage. No material known to human science could reliably withstand such impacts for the duration of an interstellar crossing. Each impact would be an explosion. Each explosion would cause damage, and the cumulative effect of countless impacts would compromise any vessel we could build. The interstellar medium is not a calm sea to be crossed, but a gauntlet of high-velocity projectiles. Shielding against dust impacts could theoretically be achieved through massive barriers at the spacecraft's bow, or through active systems that detect and deflect incoming particles. but both approaches add enormous mass and complexity to an already impossible engineering challenge. Massive bow shields would need to absorb the energy of countless impacts without allowing debris to reach the habitable sections of the spacecraft. The shields themselves would erode over time, requiring replacement or regeneration capabilities. Adding such mass means more fuel required to accelerate it, which means more mass, which requires more fuel still. Active deflection systems would need to detect particles at tremendous distances and redirect them before impact. But at 3% of light speed, particles approach at 20 million miles per hour. Detection systems would have mere milliseconds to identify threats and microseconds to deflect them. No technology we can envision could react quickly enough. The temperature of interstellar space presents additional challenges that compound over decades-long voyages. Far from any star, the ambient temperature of the cosmic microwave background radiation is approximately 2.7 Kelvin, less than 3 degrees above absolute zero. Spacecraft in this environment would radiate heat into the void, gradually cooling unless actively heated. Life support systems would need to generate warmth for centuries, maintaining human-tolerable temperatures against the relentless cold of interstellar space. Any failure in heating systems could freeze the crew within hours. Communication with Earth would become progressively more difficult as the spacecraft moved away from the solar system. Radio signals travel at light speed, meaning communications would be delayed by increasing amounts as distance grew. A message sent from Alpha Centauri would take over 4 years to reach Earth. A response would take another 4 years to return. This 8-year minimum round-trip communication time eliminates any possibility of real-time guidance from Earth-based controllers. By the time any message arrived, the situation that prompted it would be years in the past. The crew would be entirely on their own, making decisions without external input, solving problems without expert consultation. As the spacecraft approached Alpha Centauri after its century-long journey, the crew would face the challenge of slowing down from interstellar velocities. A vessel traveling at 3% of light speed cannot simply arrive at its destination. It would flash through the Alpha Centauri system in hours, too fast to enter orbit around any planet or conduct meaningful exploration. Braking from interstellar velocities requires almost as much energy as accelerating to them in the first place. The spacecraft would need to carry fuel not only for acceleration, but for deceleration, roughly doubling the total propellant requirements. For nuclear pulse propulsion, this means thousands of additional nuclear bombs, each adding mass that must itself be accelerated. The challenges compound and multiply until they reach levels that cannot be overcome through any foreseeable engineering. The distances are too great, the times are too long, the hazards are too numerous, the energy requirements are too vast. Each problem solved reveals new problems beneath it. Yet people continue to dream of reaching the stars. Science fiction fills libraries with tales of starships and interstellar colonies. Space agencies study theoretical propulsion concepts. Billionaires fund initiatives like Breakthrough Starshot, hoping to send tiny probes to Alpha Centauri within decades. These dreams persist because the alternative is accepting permanent confinement to our solar system. They persist because the stars call to something deep in human nature, some wandering instinct that cannot accept boundaries. They persist because giving up feels like a failure of imagination, a surrender to difficulties that might someday be overcome. But the laws of physics are not difficulties to be overcome. They are the rules of the universe we inhabit. Understanding those rules and the constraints they place on interstellar travel reveals why reaching Alpha Centauri may remain forever beyond human capability. The physics of propulsion, energy, and velocity create a prison more secure than any built from matter. Examining these physical constraints illuminates the true depth of our cosmic imprisonment in ways that no amount of optimism can overcome. The dream of reaching the stars runs directly into a mathematical obstacle that has tormented rocket engineers since the dawn of spaceflight. This obstacle, called the Tsiolkovsky rocket equation, governs all reaction-based propulsion with absolute authority. No engineering cleverness, no funding increases, no inspirational speeches, no technological breakthroughs can change its fundamental constraints. The equation is not a suggestion or a current limitation. It is a mathematical truth derived from the conservation of momentum, as immutable as the statement that 2 + 2 = 4. Konstantin Tsiolkovsky derived this equation in 1897, decades before the first rocket reached space. This Russian schoolteacher, working in obscurity far from the centers of scientific research, discovered the mathematical relationship that would define the limits of human ambition in space. The mathematics is elegant and simple, hiding the tyranny it imposes on interstellar dreams behind a formula that fits on a single line. The equation states that the final velocity a rocket can achieve depends logarithmically on the ratio of its initial mass to its empty mass. In plain language, this means that the speed you can reach depends on how much of your rocket is fuel versus how much is everything else. More fuel means more speed, but the relationship is not linear. It curves in ways that punish ambitious velocity targets with mathematical brutality. This logarithmic relationship creates devastating consequences for any attempt to reach high velocities. To double your final speed, you cannot simply double your fuel load. The mathematics demands exponentially more fuel for each incremental increase in velocity. A rocket that achieves 1 kilometer per second with a certain fuel load needs not twice but roughly 3 times that fuel to achieve 2 kilometers per second. Reaching 4 kilometers per second requires roughly 9 times the original fuel. The numbers escalate with terrifying speed. The equation can be written simply. Delta V equals exhaust velocity multiplied by the natural logarithm of the mass ratio. Delta V represents the change in velocity you can achieve. Exhaust velocity represents how fast your propellant leaves the engine. The mass ratio is your initial mass divided by your final mass after all fuel is burned. That natural logarithm is where the tyranny lives. Logarithms grow slowly, painfully slowly. To double your delta V, you must square your mass ratio. To triple it, you must cube your mass ratio. Achieving 10 times your exhaust velocity as delta V requires a mass ratio of over 22,000. The numbers become absurd long before they become useful for interstellar travel. Consider what this means for a spacecraft attempting to achieve 10% of light speed, roughly 18,000 miles per second. This velocity would allow reaching Alpha Centauri in approximately 43 years, still a multi-generational journey but at least within conceivable human timescales. Using conventional chemical rockets with exhaust velocities around 4.5 kilometers per second, the rocket equation demands a mass ratio so extreme that it exceeds comprehension. For every kilogram of payload you wish to accelerate to 10% of light speed using chemical rockets, you would need approximately 10 to the power of 3,000 kilograms of fuel. This number is not merely large, it is not merely astronomical, it exceeds the total mass of the observable universe by factors that cannot be meaningfully expressed. Every atom in every galaxy in existence would not provide enough fuel to accelerate a single kilogram to interstellar velocities using chemical propulsion. Chemical rockets cannot achieve interstellar velocities regardless of how much fuel you provide. The mathematics prohibits it absolutely and permanently. This is not a technology problem awaiting a clever solution. It is a fundamental physical limit that no amount of engineering can circumvent. Chemistry stores limited energy in molecular bonds. That energy, when released, accelerates exhaust gases to limited velocities. Those limited exhaust velocities, plugged into the rocket equation, produce mass ratios that make interstellar travel impossible. Understanding why chemistry imposes this ceiling requires examining what happens during rocket combustion. Rocket engines break chemical bonds in fuel molecules and reform them into exhaust products. The energy difference between the original bonds and the new bonds becomes kinetic energy in the exhaust stream. But molecular bonds contain only modest energy compared to nuclear reactions or mass energy conversion. The strongest chemical bonds available for rocket propulsion involve hydrogen and oxygen. When hydrogen burns with oxygen, the reaction releases approximately 13.4 megajoules per kilogram of propellant. This is the most energetic practical chemical reaction available for rockets. Nothing in chemistry offers significantly more energy per kilogram. This energy limitation translates directly into exhaust velocity limitations. The exhaust velocity of a rocket engine depends on how much energy each kilogram of propellant can release. Chemical rockets achieve exhaust velocities around 4 to 4.5 kilometers per second. This number represents a hard ceiling that no chemical engineering can exceed because it derives from the energy content of chemical bonds themselves. The Saturn V rocket that carried astronauts to the moon illustrates the rocket equation's constraints with stunning clarity. This engineering marvel stood 363 feet tall, taller than the Statue of Liberty. It weighed 6.2 million pounds at liftoff, most of that weight being propellant. Its 5 F1 engines produced 7.5 million pounds of thrust, enough to shake windows 50 miles away. Yet despite this overwhelming power, the Saturn V could barely manage lunar missions. The lunar module that actually landed on the moon weighed only 33,000 pounds, less than 1% of the rocket's liftoff weight. All that fuel, all that engineering, all that expense, just to place 2 astronauts on the moon for a few days before returning them to Earth. The moon lies roughly 240,000 miles from Earth. Jupiter lies approximately 2,000 times farther away. Alpha Centauri lies approximately 100 million times farther than Jupiter. The rocket equation's exponential nature means that each multiplicative increase in distance demands not merely more fuel, but exponentially more fuel, in cascading requirements that quickly exceed physical possibility. More advanced propulsion concepts offer better exhaust velocities that partially mitigate the rocket equation's tyranny. Ion engines, which accelerate ionized particles using electric fields rather than chemical combustion, achieve exhaust velocities around 30 to 50 kilometers per second. This represents an improvement of roughly tenfold over chemical rockets. Ion engines work by ionizing a propellant, typically xenon gas, and accelerating the resulting charged particles through an electric field. The particles exit the engine at tremendous velocities, providing thrust through Newton's third law. Because the exhaust velocity is so high, ion engines can achieve impressive total velocity changes with modest propellant loads. The Dawn spacecraft demonstrated ion propulsion's potential during its mission to the asteroid belt. Dawn used ion engines to travel from Earth to the asteroid Vesta, orbit Vesta for over a year, then depart and travel to the dwarf planet Ceres. This tour of 2 separate bodies would have been impossible with chemical propulsion given the spacecraft's mass constraints. But ion engines suffer from a critical limitation that makes them impractical for crewed missions. While they achieve high exhaust velocities, they produce extremely low thrust. Dawn's ion engine produced about 90 millinewtons of thrust, equivalent to the weight of a few sheets of paper pressing on your hand. This gentle push, sustained over months and years, eventually accelerated the spacecraft to significant velocities. The mathematics remains punishing even with ion propulsion. Mass ratios for interstellar velocities drop from universe-exceeding impossibility to merely civilization-exceeding impossibility. Ion engines represent an improvement, not a solution. They could potentially enable faster travel within the solar system, but cannot bridge the gap to the stars. Nuclear thermal rockets offer another incremental improvement. These engines heat propellant using nuclear reactor cores rather than chemical combustion. The propellant, typically hydrogen, flows through channels in the reactor, absorbs heat from nuclear fission, and expands through a nozzle to produce thrust. Nuclear thermal rockets achieve exhaust velocities around 8 to 9 kilometers per second, roughly double chemical rocket performance. NASA developed and tested nuclear thermal engines during the 1960s under the NERVA program. These engines successfully operated on test stands, demonstrating that nuclear thermal propulsion was technically feasible. The NERVA engines produced approximately 75,000 pounds of thrust, with a specific impulse of over 800 seconds. They could have reduced Mars transit time significantly compared to chemical propulsion. Several mission studies proposed using nuclear thermal rockets for crewed Mars exploration, but for interstellar travel, nuclear thermal propulsion remains hopelessly inadequate. Doubling exhaust velocity helps, but it does not transform the fundamental mathematics from impossible to possible. The improvement is like reducing a prison sentence from infinity to half of infinity. You are still never getting released. Nuclear pulse propulsion represents a more radical approach that could theoretically achieve truly impressive velocities. Project Orion, studied from 1958 to 1963, proposed using nuclear explosions behind a spacecraft to provide thrust. Each explosion would push against a massive steel plate, and shock absorbers would smooth the impulses into continuous acceleration. The concept sounds insane, and by conventional engineering standards it's sun. But the physics works. Nuclear explosions release enormous energy compared to chemical reactions. A spacecraft riding nuclear pulses could theoretically achieve exhaust velocities exceeding 20 kilometers per second for fission bombs, or much higher for fusion bombs. Freeman Dyson, one of the physicists who worked on Project Orion, calculated that a spacecraft using nuclear pulse propulsion could theoretically achieve velocities of 3 to 5% of light speed. At such velocities, Alpha Centauri could be reached in approximately 100 to 150 years, still multi-generational, but with inconceivable human timescales. Project Orion was never built for reasons that had nothing to do with physics. Exploding nuclear bombs in Earth's atmosphere would create catastrophic radioactive fallout. The Partial Test Ban Treaty of 1963 prohibited atmospheric nuclear explosions, effectively killing the project. Even before the treaty, the political and environmental implications of nuclear pulse propulsion were obvious deal-breakers. The technology could only be assembled and operated far from Earth, in deep space where fallout would not contaminate our planet. But constructing 1,000-ton spacecraft in orbit requires industrial capabilities humanity has never developed. The International Space Station, built over decades at enormous cost, masses only 420 tons. An Orion spacecraft would need to be far larger. The number of nuclear bombs required for an interstellar voyage would number in the hundreds of thousands or millions. Manufacturing, storing, and safely deploying such quantities exceeds any logistical capability humanity has demonstrated. The cost would consume the entire economic output of human civilization for decades. Fusion propulsion offers theoretical promise that exceeds nuclear fission by significant margins. Fusion reactions, which combine light atomic nuclei to form heavier elements, release energy through the same process that powers stars. The energy released per kilogram of fuel exceeds chemical reactions by factors of millions. Deuterium-tritium fusion releases approximately 340 trillion joules per kilogram of fuel. Compare this to chemical propulsion's 13 million joules per kilogram. Fusion offers roughly 25 million times more energy per kilogram than the best chemical reactions. This enormous energy density could theoretically enable exhaust velocities approaching 1% of light speed. At such exhaust velocities, the rocket equation becomes dramatically more forgiving. Achieving 10% of light speed would require mass ratios measured in thousands rather than numbers with thousands of digits. Difficult, but conceivably achievable for a sufficiently advanced civilization. But fusion propulsion does not exist except in theoretical papers and science fiction. Despite 70 years of research and tens of billions of dollars in investment across multiple nations, controlled fusion power generation remains experimental. No fusion reactor has ever produced net energy output exceeding its energy input for more than brief moments. The engineering challenges of fusion propulsion extend far beyond achieving fusion reactions. A fusion rocket would need to contain plasma at temperatures exceeding 100 million degrees Celsius while directing that plasma to produce useful thrust. At such temperatures, matter exists in a completely ionized state. Electrons stripped from atoms, nuclei moving at tremendous velocities. No material can directly contain fusion plasma. Any physical wall touching plasma at 100 million degrees would vaporize instantly, contaminating the plasma and quenching the fusion reaction. The plasma must be confined using magnetic fields that create invisible bottles, holding the superheated material away from all physical surfaces. Tokamak reactors and stellarators use complex magnetic field geometries to confine plasma for experimental fusion research. These devices fill buildings with superconducting magnets cooled to near absolute zero. They consume enormous electrical power just to maintain their magnetic configurations. Translating such technology into a spacecraft that must operate reliably for decades presents challenges beyond current engineering capability. Alternative fusion approaches using laser compression face different but equally daunting obstacles. Inertial confinement fusion, researched at facilities like the National Ignition Facility, uses powerful laser arrays to compress fuel pellets until fusion ignites. The lasers must deliver millions of joules of energy in billionths of a second, focused on targets smaller than pencil erasers. The National Ignition Facility achieved fusion ignition in December 2022, producing more energy from fusion than the lasers delivered to the target. This represented a historic milestone after decades of research. But the facility consumes far more total energy than the fusion reaction produces when all systems are considered. And the facility fills a building the size of a sports stadium, hardly suitable for spacecraft propulsion. Antimatter propulsion represents the theoretical maximum for any propulsion system that carries its own fuel. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy. According to Einstein's famous equation, E equals mc squared. This perfect efficiency exceeds fusion by a factor of roughly 140. Nothing in physics permits more complete conversion of mass into energy. 1 kilogram of matter annihilating with 1 kilogram of antimatter releases approximately 90 petajoules of energy, equivalent to roughly 21 megatons of TNT. This exceeds the largest nuclear weapon ever tested. Such energy densities could theoretically enable exhaust velocities approaching the speed of light itself. With antimatter, the rocket equation finally becomes manageable for interstellar velocities. A spacecraft carrying appropriate amounts of matter and antimatter could theoretically achieve velocities at significant fractions of light speed if all the annihilation energy could be captured and directed as thrust. But antimatter does not exist naturally in our solar system or anywhere else in the observable universe in useful quantities. The Big Bang produced equal amounts of matter and antimatter, but some asymmetry caused nearly all antimatter to annihilate with matter in the universe's first moments. What remains is a cosmos composed almost entirely of normal matter. Every microgram of antimatter needed for spacecraft propulsion must be manufactured using particle accelerators. These facilities collide particles at tremendous energies, occasionally producing matter-antimatter pairs from the collision energy. The process is fantastically inefficient, requiring far more energy to produce antimatter than the antimatter itself stores. Current global antimatter production at all particle physics facilities combined amounts to approximately 10 to 15 nanograms per year. A nanogram is 1 billionth of a gram. At this production rate, accumulating 1 gram of antimatter would require approximately 100 million years. A practical interstellar mission would require tons of antimatter, not nanograms or grams. The cost of antimatter production currently exceeds $60 trillion per gram. This single gram would release energy equivalent to roughly 43 kilotons of TNT if annihilated, comparable to a nuclear weapon. But 1 gram would provide negligible propulsion for an interstellar spacecraft. The expense of producing useful quantities would exceed the total economic output of human civilization throughout all of history. Even if antimatter could somehow be produced affordably, storing it presents nearly insurmountable challenges. Antimatter must never contact normal matter under any circumstances. When an antiproton touches a proton, both particles annihilate in a burst of energy. Current technology can store antiprotons and positrons using magnetic traps that prevent the particles from touching container walls. These penning traps hold small numbers of antiparticles using combinations of electric and magnetic fields, but storage durations are measured in minutes at best, and quantities are measured in nanograms at most. Storing significant quantities of antimatter for decades-long interstellar voyages exceeds current capabilities by factors beyond estimation. The containment systems would need to operate flawlessly through launch vibrations, cosmic ray impacts, equipment failures, and countless other potential disruptions. Any breach would result in catastrophic annihilation. The energy release from antimatter annihilation also creates propulsion challenges. When matter and antimatter annihilate, they do not produce hot exhaust gases that can be directed through a nozzle. The annihilation products depend on what particles are involved. Electron-positron annihilation produces gamma rays with energies around 500,000 electron volts each. Proton-antiproton annihilation produces showers of particles called pions, which quickly decay into muons, then electrons, positrons, neutrinos, and gamma rays. Much of the annihilation energy emerges as gamma radiation. Gamma rays are extremely difficult to direct or reflect. They pass through most materials without interacting. No mirror can reflect gamma rays as easily as visible light. No nozzle can direct gamma rays as exhaust. A significant fraction of antimatter's theoretical energy advantage evaporates when confronting the physics of what annihilation actually produces. Some proposals suggest using the gamma rays to heat a working fluid that could then be expelled as conventional exhaust. But capturing gamma rays efficiently requires materials and geometries that do not exist. Most gamma radiation would simply escape into space, wasting energy that should have provided thrust. These propulsion limitations reveal a disturbing truth about interstellar travel. Every known propulsion technology fails to provide a practical path to the stars. Chemical rockets are fundamentally and permanently inadequate. Nuclear thermal propulsion improves performance modestly, but cannot bridge interstellar distances. Ion engines offer efficiency, but impossibly low thrust. Nuclear pulse propulsion might work, but faces insurmountable practical obstacles. Fusion and antimatter remain theoretical after decades of research. Propulsion is only half the challenge. Even if we could somehow achieve the required velocities, slowing down at the destination presents equally daunting requirements governed by the same tyrannical physics. A spacecraft that accelerates to 10% of light speed must carry enough fuel to decelerate at the destination if it wishes to do more than flash through the target system at 18,000 miles per second. Without braking, the spacecraft would cross the Alpha Centauri system in hours, far too fast to enter orbit around any planet or conduct meaningful exploration. Braking requires expending propellant to produce thrust, opposing the direction of travel. The rocket equation applies to deceleration exactly as it applies to acceleration. If you need a mass ratio of 1,000 to accelerate to cruising velocity, you need another mass ratio of 1,000 to decelerate. But here is where the mathematics becomes truly cruel. These mass ratios multiply rather than add. You must accelerate your deceleration fuel along with your payload. The deceleration fuel is part of the payload during acceleration. A combined acceleration-deceleration mission requires mass ratios that multiply together, producing requirements that make even theoretically possible journeys practically impossible. Some proposals avoid the braking problem by using external propulsion systems. Light sails, large reflective surfaces pushed by powerful lasers, could theoretically accelerate spacecraft without requiring onboard propellant. The Breakthrough Starshot initiative proposed exactly this approach. Announced in 2016, with $100 million in initial funding from billionaire Yuri Milner, Breakthrough Starshot proposed accelerating thousands of tiny spacecraft to 20% of light speed using ground-based laser arrays. Each spacecraft would weigh only grams and measure only centimeters across. At 20% of light speed, they would reach Alpha Centauri in approximately 20 years. The concept elegantly sidesteps the rocket equation by not using rockets at all. The laser array remains on Earth, pushing the sail with photon pressure. The spacecraft carries no propellant and suffers no mass ratio penalty. In principle, any velocity below light speed could be achieved with sufficient laser power, but breakthrough Starshot spacecraft would be unable to slow down at the destination. No laser array exists at Alpha Centauri to provide braking thrust. The tiny spacecraft would race through the target system at 20% of light speed, over 100 million miles per hour. They would cross the distance from Alpha Centauri A to Proxima Centauri in a few days. This is not interstellar travel in any meaningful sense. It is a glorified camera throw, lobbing imaging systems at a target too distant to examine closely. No human or human artifact would remain at Alpha Centauri. Nothing could be studied in detail. No colony could be established. No resources could be utilized. Even this modest camera throw faces enormous engineering challenges. Accelerating gram-scale spacecraft to 20% of light speed requires laser arrays outputting 100 gigawatts for several minutes. This power level exceeds the total electrical generation capacity of most countries. The United States generates approximately 450 gigawatts of electrical power total, and most of that is committed to existing uses. The laser array would need to focus this enormous power on sails measuring meters across while those sails accelerate to over 100 million miles per hour. The beam must remain perfectly centered on the sail throughout the acceleration phase. Any misalignment would cause the tiny spacecraft to tumble out of the beam or vaporize from uneven heating. Atmospheric turbulence distorts laser beams, requiring adaptive optics to compensate. Current adaptive optic systems can correct for turbulence, affecting astronomical observations. Maintaining beam quality for power transmission to accelerating spacecraft presents challenges of a different magnitude entirely. The spacecraft themselves would need to survive acceleration forces potentially exceeding 60,000 times Earth's gravity during the brief acceleration phase. Every component would need redesign for such extreme conditions. Cameras, communication systems, power supplies, and data storage would all need to function after experiencing forces that would crush any conventional device. After surviving acceleration, the tiny spacecraft would face 20 years of travel through interstellar space. At 20% of light speed, collisions with dust grains would be even more energetic than at lower velocities. Each impact would be a small explosion. Breakthrough Starshot proposes sending thousands of spacecraft precisely because most would be destroyed during the journey. Even assuming some spacecraft survived, their scientific return would be minimal. Gram-scale spacecraft cannot carry sophisticated instruments. They cannot enter orbit around Proxima b. They cannot deploy landers or rovers. They cannot analyze atmospheric composition in detail, or search for biosignatures with the sensitivity that detecting life would require. Alternative propulsion concepts exist in theoretical physics, but none have demonstrated any path to physical implementation. The Alcubierre warp drive, proposed in 1994 by Mexican physicist Miguel Alcubierre, describes a theoretical method for faster-than-light travel that does not technically violate Einstein's relativity. The concept involves contracting space ahead of a spacecraft while expanding space behind it. The spacecraft itself remains stationary within a bubble of flat spacetime, while the bubble moves through the universe at arbitrary velocity. From outside perspectives, the spacecraft appears to travel faster than light. From the spacecraft's perspective, it never exceeds light speed locally. This elegant mathematics has inspired countless science fiction stories, but the concept requires exotic matter with negative energy density, a substance that has never been observed and may not exist. The energy requirements for even a small warp bubble range from the mass energy of Jupiter to the mass energy of the observable universe, depending on the analysis. Wormholes, theoretical tunnels through space-time connecting distant points, appear in solutions to Einstein's field equations. Science fiction has embraced wormholes as convenient plot devices for rapid interstellar travel. The mathematics describes geometries where space folds back on itself, creating shortcuts between locations separated by light years. But creating or stabilizing a wormhole would require the same exotic matter as the warp drive. Natural wormholes, if they exist, would be submicroscopic and would collapse before anything could pass through. Enlarging and stabilizing a wormhole for passage would require manipulating space-time with energies and technologies beyond anything we can conceive. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, suggested a clever solution to the fuel problem. A spacecraft would deploy enormous electromagnetic scoops to collect interstellar hydrogen, then fuse this hydrogen for propulsion. The fuel would come from space itself, eliminating the need to carry propellant from Earth. Subsequent analysis revealed fatal flaws in this elegant concept. Interstellar hydrogen is too sparse. A ramscoop would need to collect hydrogen from volumes measured in thousands of cubic kilometers per second. The electromagnetic fields required to funnel this hydrogen would create drag that exceeds any thrust the collected fuel could provide. The ramjet would decelerate rather than accelerate. The physics prison surrounding humanity is comprehensive and secure. No known propulsion technology can achieve practical interstellar velocities within human timescales. No theoretical technology has demonstrated any path from mathematical equations to physical hardware. The laws of physics permit interstellar travel only in abstractions, not in engineering reality. But even if we could somehow propel spacecraft between stars through means we cannot currently imagine, the journey would still face barriers that physics cannot solve and engineering cannot circumvent. The rockets might work, but the passengers would not survive. The human body and mind evolved for conditions on Earth's surface, not for interstellar voids that would kill us long before we reached any destination. Space is trying to kill you. This is not metaphor or exaggeration. Every moment an astronaut spends beyond Earth's protective magnetic field, invisible particles pierce their body, damaging DNA, killing cells, accumulating harm that no medicine can fully reverse. This radiation environment represents perhaps the most insurmountable barrier to interstellar travel. A biological constraint that cannot be engineered around without technologies we do not possess and may never develop. The universe is flooded with high-energy particles streaming through every cubic meter of space. These particles have been traveling since the deaths of ancient stars, accelerated to tremendous velocities by the most violent events in cosmic history. Solar flares release bursts of protons, traveling at significant fractions of light speed. Galactic cosmic rays, accelerated by distant supernovae and the shock waves surrounding black holes, carry energies that dwarf anything humans can produce in our largest particle accelerators. These particles pass through spacecraft hulls as if those hulls were made of tissue paper. The aluminum and composite materials that protect astronauts from vacuum and temperature extremes provide essentially no protection against galactic cosmic rays. The particles simply punch through, depositing energy as they go, leaving trails of ionized atoms and damaged molecules in their wake. On Earth's surface, we remain blissfully unaware of this constant cosmic bombardment because multiple shields protect us. The atmosphere absorbs most cosmic radiation before it reaches ground level, with air molecules scattering and stopping incoming particles across miles of protective gas. Earth's magnetic field deflects charged particles, funneling them toward the polar regions, where they create the shimmering auroras that ancient peoples interpreted as messages from gods. The depth of our atmospheric protection is staggering when quantified. The atmosphere above your head provides shielding equivalent to approximately 3 feet of solid concrete or 10 feet of water. This mass absorbs the vast majority of cosmic radiation, allowing only a tiny fraction to reach the surface. At sea level, you receive roughly 300 millirem of cosmic radiation per year. Climb to airplane cruising altitude, and that dose increases significantly because less atmosphere shields you. The combined protection of atmosphere and magnetic field reduces surface radiation to levels our biology can tolerate. Life on Earth evolved within this protected environment over billions of years. Our cells developed repair mechanisms calibrated to the modest radiation doses that penetrate our planetary shields. These repair mechanisms work constantly, fixing DNA damage as it occurs, maintaining cellular integrity against the small radiation doses we cannot avoid. Remove those shields, and our biology faces challenges it never evolved to handle. The repair mechanisms become overwhelmed. Damage accumulates faster than cells can fix it. The consequences manifest in ways that threaten every organ system in the human body. In deep space, beyond Earth's protective magnetic field, these protections vanish completely. Astronauts traveling beyond low Earth orbit enter an environment where galactic cosmic rays arrive from every direction continuously. There is no day or night cycle of radiation exposure. There is no shelter that blocks the most energetic particles. There is only constant bombardment that never stops. Galactic cosmic rays present the most dangerous long-term hazard because they are constant, unavoidable, and enormously energetic. These particles, mostly protons and helium nuclei stripped of their electrons, carry energies exceeding 1 billion electron volts. Some carry energies exceeding 1 trillion electron volts, more than the Large Hadron Collider can produce through deliberate acceleration. The source of galactic cosmic rays lies in the most violent events the universe produces. Supernovae, the explosive deaths of massive stars, accelerate particles through expanding shock waves. The remnants of these explosions continue accelerating particles for thousands of years after the initial explosion. Some cosmic rays originate from the accretion disks around black holes, where matter falling toward the event horizon reaches extreme velocities before being flung outward. These particles have traveled for millions of years across the galaxy before encountering Earth. They arrive from every direction with no warning. Unlike solar radiation, which comes from a single direction and varies with solar activity cycles, galactic cosmic rays maintain a constant baseline that cannot be predicted or avoided. When galactic cosmic rays strike human tissue, they do not simply pass through harmlessly. The particles interact with atoms in cells, creating cascades of secondary particles that spread damage through surrounding tissue, like shrapnel from an explosion. A single cosmic ray can damage dozens of cells along its path, breaking DNA strands, disrupting cellular machinery, and triggering inflammatory responses. The heaviest cosmic ray particles, called HZE ions, cause the most severe damage. These are the nuclei of heavy elements like iron, accelerated to relativistic velocities by cosmic events. When an HZE ion passes through tissue, it leaves a track of destruction tens of micrometers wide. Every molecule in its path is ionized or destroyed. The affected cells either die immediately or suffer damage that may lead to cancer years later. The human body possesses remarkable repair mechanisms that can fix most radiation damage if given time. Enzymes constantly patrol DNA strands, detecting damage and initiating repair processes. Single-strand DNA breaks are typically repaired within hours. The cellular machinery for maintaining genetic integrity has evolved over billions of years to handle Earth's surface radiation levels. But these repair mechanisms evolved to handle Earth's surface radiation levels, not the constant bombardment of interstellar space. Over years and decades of exposure to galactic cosmic rays, damage would accumulate faster than biology could repair it. The repair machinery would fall behind, overwhelmed by the constant influx of new damage. Current spacecraft provide minimal shielding against galactic cosmic rays because the particles are so energetic that stopping them requires massive barriers. Effective shielding would require water walls several feet thick, or aluminum barriers measuring feet rather than inches across. The mass of such shielding would be measured in tons or tens of tons for a crew compartment. Adding such mass to a spacecraft cascades through the rocket equation with devastating effect. More shielding mass means more fuel required to accelerate that mass. More fuel means more total mass. More total mass means even more fuel in the exponential spiral that makes interstellar travel impossible. Radiation protection and propulsion requirements create competing constraints that cannot be simultaneously satisfied. Active shielding using powerful magnetic fields has been proposed as an alternative to mass shielding. The concept mirrors Earth's natural protection. Generate a magnetic field strong enough to deflect charged particles away from the spacecraft, creating an artificial magnetosphere that substitutes for planetary protection. But generating magnetic fields strong enough to deflect galactic cosmic rays would require superconducting magnets of enormous size and power consumption. The required field strengths approach those found in particle accelerators, facilities that fill buildings and consume the electrical output of small cities. Miniaturizing such technology for spacecraft remains beyond current engineering capability. Even perfect magnetic shielding would not stop all dangerous particles. Neutral particles like neutrons carry no charge and cannot be deflected by magnetic fields. When cosmic rays impact spacecraft structures, they produce showers of secondary particles, including neutrons that would penetrate any magnetic shield. Complete protection remains impossible regardless of the shielding approach employed. The central nervous system proves especially vulnerable to radiation damage in ways that threaten the very capabilities astronauts would need for interstellar missions. Neurons, the information processing cells of the brain, are essentially irreplaceable in adult humans. Unlike skin cells or blood cells, which regenerate continuously throughout life, neurons persist for decades. Damage to neurons accumulates without the regeneration that other tissues can achieve. Studies of cosmic ray effects on animal brains have revealed disturbing results that should concern anyone contemplating multi-year space voyages. Researchers at the University of California, Irvine, exposed mice to radiation levels comparable to those astronauts would experience on interstellar journeys. The results demonstrated significant cognitive impairment across multiple measures. Irradiated mice showed reduced memory, measured by decreased ability to recognize objects they had previously encountered. Their curiosity decreased, measured by reduced exploration of novel environments. Their anxiety increased, measured by avoidance behaviors in standard psychological tests. Most disturbingly, these changes persisted long after radiation exposure ended. The damage was not temporary impairment that recovered with time. It represented permanent alteration of brain function. Examination of the mice's brains revealed physical changes underlying these behavioral deficits. Dendritic spines, the tiny protrusions on neurons where synaptic connections form, were reduced in number and complexity. The architecture of neural networks had been degraded by radiation exposure. The physical substrate of thought and memory had been damaged. Human astronauts on multi-year interstellar voyages would face similar cognitive degradation if animal models accurately predict human responses. Their ability to solve problems would decline as neurons accumulated radiation damage. Their capacity to maintain complex equipment would diminish. Their skill at navigating the inevitable interpersonal conflicts of small group isolation would deteriorate precisely when such skills became most critical. By the time an interstellar crew reached any destination, they might lack the mental capability to accomplish mission objectives that motivated the journey. The sharp young engineers and scientists who departed Earth would arrive as cognitively impaired versions of themselves, their intellects degraded by decades of continuous radiation exposure. Cancer risk represents another certain consequence of prolonged space radiation exposure that no mission planning can avoid. When radiation damages DNA, the repair mechanisms sometimes introduce errors. These errors can accumulate over time, eventually transforming a normal cell into a cancerous one that divides without limit. Current estimates suggest that astronauts on 18-month Mars missions would face lifetime cancer risk increases of approximately 5% compared to remaining on Earth. This elevated risk is considered marginally acceptable for such historic achievements, though debates about acceptable risk levels continue among space medicine professionals. Multi-decade interstellar journeys would push these risks far higher, potentially into ranges where most crew members would develop malignancies during the voyage. The relationship between radiation exposure and cancer risk appears to be roughly linear at the doses involved. Double the exposure, roughly double the risk. Multiply the exposure by factors of 10 or more, and cancer becomes not a risk but a near certainty. A crew departing for Alpha Centauri would embark knowing that the majority of them would likely develop cancers before reaching the destination. This foreknowledge would colour the entire mission psychology in ways difficult to predict. Every ache, every unexplained symptom would trigger anxiety about whether the cancer had finally appeared. Medical treatment capabilities aboard any conceivable interstellar spacecraft would be severely limited compared to Earth-based oncology. Chemotherapy requires toxic drugs that must be manufactured fresh, as they degrade over time. Many chemotherapy protocols require specific drug combinations tailored to specific cancer types, requiring extensive pharmaceutical supplies. Radiation therapy for cancer requires precisely targeted radiation sources, linear accelerators that focus beams on tumor sites while minimizing damage to surrounding tissue. These machines fill hospital rooms and require expert operation. Maintaining and operating such equipment for decades aboard a spacecraft presents enormous challenges. Surgical removal of tumors requires operating rooms, trained surgeons, anesthesia equipment, and recovery facilities. Complex surgeries would need to be performed in microgravity or artificial gravity environments, unlike anything surgeons train in on Earth. The physiological changes of long-duration spaceflight would alter how bodies respond to surgical intervention in ways we cannot fully predict. Many astronauts would simply die from cancers they could not adequately treat. The spacecraft would need provisions for caring for the terminally ill and for disposing of bodies in ways that did not compromise life support systems or crew morale. Funeral rituals would need to evolve for circumstances never faced by any human culture throughout history. Even astronauts who avoided cancer would face accelerated aging from cumulative radiation damage. The cellular systems involved in biological aging are particularly sensitive to radiation effects. Telomeres, the protective caps on chromosome ends that shorten with each cell division and with age, erode faster under radiation exposure. Stem cell populations that replenish aging tissues throughout life would be depleted by radiation damage. The regenerative capacity that allows human bodies to maintain themselves would be progressively compromised. Inflammatory responses associated with aging would be chronically activated by continuous cellular damage. A 30-year-old astronaut might complete an interstellar voyage with the biological age of a 60 or 70-year-old. Their remaining lifespan would be dramatically shortened compared to contemporaries who remained on Earth. The interstellar voyage would steal decades of life even from those who survived it without developing cancer. Beyond radiation, the human body faces other challenges in extended spaceflight that complicate any interstellar mission architecture. Microgravity causes progressive bone loss at rates approaching 1 to 2% per month in the spine and hip. Bones that evolved to support body weight against gravity begin dissolving when that stress disappears. Astronauts on the International Space Station exercise for 2 hours daily, using specialized resistance equipment designed to stress bones and muscles despite the absence of gravity. This rigorous regimen reduces but does not eliminate physiological deconditioning. Astronauts returning from 6-month missions require weeks of rehabilitation before fully recovering Earth normal function. Muscles atrophy without the constant work of supporting body weight. Heart muscle, which pumps blood against gravity on Earth, becomes deconditioned in microgravity where blood flows more easily toward the head. Cardiovascular fitness declines, even with exercise countermeasures. Fluid redistribution toward the head causes increased intracranial pressure that has affected astronaut vision. Some astronauts on long-duration missions have experienced permanent vision changes, with flattening of their eyeballs and swelling of optic nerves. The mechanism is not fully understood, and no effective countermeasure has been developed. An interstellar voyage lasting decades would require artificial gravity to maintain human health over such extended durations. Rotating spacecraft sections could provide centrifugal acceleration that simulates gravitational force. Science fiction has depicted such rotating habitats for generations, But rotating spacecraft present their own engineering challenges. The rotation rate required to produce Earth normal gravity depends on the diameter of the rotating section. Small diameter sections must spin rapidly, several rotations per minute. This rapid rotation creates Coriolis effects as objects move within the rotating frame. Coriolis forces would make simple actions disorienting. Walking in the direction of rotation would make you feel heavier. Walking against rotation would make you feel lighter. Reaching for objects would require correcting for apparent deflections. Throwing or catching anything would become unexpectedly difficult. Inner ear balance systems would face constant conflicting signals. Looking up or down would create spinning sensations as the semicircular canals responded to rotation. Nausea and disorientation could be chronic problems for crew members unable to adapt. Large spacecraft could spin more slowly, reducing Coriolis effects to tolerable levels. But large spacecraft require vastly more structural mass, which requires more propulsion capability, which adds more mass in the familiar cascade of interrelated constraints. Psychological challenges compound physical health concerns in ways that multiply the difficulty of long-duration missions. Humans are social animals who evolved in communities ranging from dozens to hundreds of individuals. Our psychology expects regular contact with varied people, changing environments, new experiences, and connections to larger social structures. Extended isolation and confinement produce predictable psychological problems that no screening or training can entirely prevent. Depression rates increase with mission duration. Anxiety disorders emerge even in previously healthy individuals. Interpersonal conflicts intensify as small irritations accumulate into major grievances over months and years. Antarctic research stations provide one of the closest Earth-based analogies to deep space isolation. Small crews, sometimes as few as 12 people, spend the polar winter months in complete isolation when weather prevents any evacuation or resupply. These stations have experienced serious psychological problems despite regular communication with the outside world. A phenomenon called winter over syndrome affects Antarctic personnel with symptoms including depression, irritability, hostility, insomnia, and cognitive impairment. Even knowing that rescue would become possible when weather improved does not prevent these psychological effects. The isolation itself produces predictable degradation. Submarine crews face similar isolation challenges, confined for months underwater in spaces even more cramped than spacecraft. Despite extensive psychological screening before deployment and regular support during missions, submarines have experienced crew conflicts and psychological breakdowns during extended patrols. The confined environment, artificial lighting, and separation from normal life patterns create psychological stresses that screening cannot fully predict. An interstellar crew would face isolation far more complete and permanent than any Antarctic researcher or submarine sailor has ever experienced. Communication delays measured in years would eliminate any possibility of real-time contact with Earth. By the time any advice arrived from Earth-based psychologists, the crisis that prompted the request would be years in the past. The knowledge that no rescue was possible would weigh on every crew member, regardless of psychological preparation. Antarctic researchers know that spring will eventually come. Submarine crews know that their patrol will end. Interstellar travelers would know that they had committed to decades of confinement, with no possibility of early return, and no external assistance if circumstances became unbearable. Generation ships designed to sustain populations across multiple lifetimes would face unique psychological challenges unknown to single-generation crews. Children born aboard such vessels would never know any environment except the spacecraft's interior. They would grow up within metal walls, breathing recycled air, eating food grown under artificial lights. The natural world would be a collection of images and recordings, not lived experience. Earth would become mythology for spaceborne generations. Stories told by grandparents who themselves had only childhood memories of the homeworld would fade into legend. The blue skies, open horizons, wind and rain that shaped human psychology over millions of years of evolution would become abstract concepts without visceral meaning. These spaceborne generations would inherit a mission they never chose, traveling toward a destination selected before their birth by ancestors they never knew. The mission objectives would be inherited obligations, not personal choices. How would these individuals perceive their situation? Would they accept parameters established by others, or would they develop their own priorities? Human history provides disturbing precedents for what happens to multi-generational communities, isolated from outside contact. Religious movements founded with specific purposes routinely splinter into competing factions within a few generations. Political systems designed to persist collapse under the weight of accumulated grievances and changing circumstances. The Pilgrims who founded Plymouth Colony sought to establish a specific religious community with particular values and practices. Within 3 generations, their descendants had largely abandoned the strict religious observance that motivated the original settlement. The grandchildren and great-grandchildren lived lives that would have been unrecognizable to their ancestors. Expecting any human community to maintain unified purpose across the multiple generations required for interstellar travel asks more than human nature has demonstrated capacity to deliver. The original mission planners would be dead long before arrival. Their intentions would be preserved only in records that subsequent generations might interpret differently, ignore completely, or actively reject. Social breakdown on an interstellar generation ship could take many forms that no mission planning can anticipate or prevent. Factions might develop competing visions for the mission's purpose. Some might wish to continue toward the original destination. Others might advocate turning back, even knowing that return would take generations more. Still others might reject the entire framework of destination-oriented thinking. Resources might be hoarded by elite groups who claimed authority through descent from original crew members or through control of essential ship systems. Class divisions have characterized every large human community in recorded history. Those who controlled life support, food production, or navigation would possess power that others would resent and seek to challenge. Violence could erupt from accumulated grievances with no external authority to restore order. Mutiny aboard historical sailing ships sometimes resulted in the killing of officers and complete deviation from original voyage plans. The mutineers on the Bounty murdered their captain and abandoned their mission entirely. Some established their own community on a remote island with eventually tragic results. Generation ships would have no external authority to prevent or punish such events. No navy would arrive to restore order. No court would try the perpetrators. Whatever social dynamics emerged, whether constructive or destructive, would play out to their conclusions without outside intervention. Even without dramatic breakdowns, gradual cultural drift could undermine mission objectives. Knowledge essential for mission success might not be transmitted effectively across generations. Technical skills might atrophy if education systems failed to maintain quality. The engineering expertise needed to maintain spacecraft systems might fade if younger generations prioritized different values or found technical education boring. Languages would evolve over centuries of isolation. Technical terminology established at departure might lose meaning or be reinterpreted in ways that cause dangerous misunderstandings. Maintenance manuals written in departure-era language might become increasingly difficult to interpret as centuries passed. Engineering reliability over multi-decade timescales represents another, apparently insurmountable barrier to interstellar travel. No human technology has ever been designed to operate continuously for over a century without external resupply and maintenance. The oldest functioning machines on Earth require constant attention from skilled technicians using replacement parts manufactured in extensive industrial systems. Medieval clocks that still operate have been rebuilt multiple times. Every component has been replaced, often many times over. What persists is the design, not the original physical machinery. An interstellar spacecraft would need to operate for decades without access to spare parts manufactured on Earth. Every component would need to be either perfectly reliable for the entire mission duration, which no human technology has ever achieved, or repairable using only resources available aboard the spacecraft. The International Space Station provides a cautionary example. Despite its relatively short operational life of about 25 years, the station has required constant maintenance and regular resupply of replacement parts. Components fail, software glitches occur, and systems degrade. The station only continues operating because cargo ships deliver spare parts and astronauts perform repairs using those Earth-manufactured components. An interstellar spacecraft would need manufacturing capability to produce replacement parts for any system that might fail. This requires machine tools, raw materials, and personnel trained in every relevant trade. The supply chain that supports modern technology would need to be compressed into a single vessel. Consider what manufacturing even simple objects requires. Metal parts need mining, smelting, forming, and machining. Electronic components need refined materials, clean rooms, and specialized equipment. Seals, gaskets, and flexible materials need chemical processing facilities. Every system aboard a spacecraft depends on supply chains that stretch across Earth's industrial civilization. Replicating these capabilities aboard a spacecraft would require a population of thousands trained in diverse technical specialties. Even with advanced automation and artificial intelligence, certain maintenance tasks would require human hands. Complex repairs often demand improvisation and problem-solving that current technology cannot match. The accumulation of minor failures over decades could prove as deadly as single catastrophic events. Each small problem solved would consume resources and attention that might be needed elsewhere. The spacecraft would age like any complex machine, developing quirks and weaknesses that gradually degraded mission capability until eventual fatal failure. What hope remains for interstellar travel given these seemingly insurmountable barriers? Some researchers propose sending machine intelligences rather than biological humans. Robotic spacecraft could tolerate radiation exposure that would kill humans within years. They would not require food, water, or breathable atmosphere. They could be placed in hibernation during transit and activated upon arrival. But robotic missions face their own limitations. Current artificial intelligence cannot match human problem-solving for genuinely novel situations. A robotic probe arriving at Alpha Centauri might encounter circumstances that its programmers never anticipated. Without the flexibility to adapt to unexpected challenges, the mission might fail despite successfully traversing the interstellar void. Communication delays would prevent Earth-based controllers from guiding robotic decisions. Every response would arrive over 4 years after the situation that prompted it. By the time advice reached the probe, conditions might have changed entirely. The robots would need to operate autonomously, making judgments that their designers never anticipated based on circumstances never simulated. If future artificial intelligence achieves genuine human-level intelligence and flexibility, troubling ethical questions arise about its use for interstellar exploration. Would truly intelligent machines agree to multi-decade journeys for humanity's benefit? The ethics of creating intelligent beings, specifically for interstellar servitude, becomes troubling when those beings can genuinely understand their situation. Biological modifications to humans represent another speculative path forward. Genetic engineering might eventually create humans resistant to radiation damage, requiring minimal food, or capable of suspended animation during transit. Such modifications lie far beyond current capabilities, but might become possible as biotechnology advances. Creating radiation-resistant humans would require modifications to fundamental cellular processes shared across all complex life on Earth. DNA repair mechanisms would need enhancement beyond anything evolution has produced. The changes required might alter human biology so profoundly that the resulting beings would constitute a new species rather than modified humans. Suspended animation could reduce life support requirements and psychological challenges if humans could be made to sleep through multi-decade voyages. But no reliable human hibernation technology exists despite decades of research. The metabolic changes required to sustain life during extended hibernation remain poorly understood. Animals that naturally hibernate do so for months, not decades. The most radical proposals abandon biological humanity entirely in favor of digital existence. Mind uploading, the hypothetical transfer of human consciousness into computer substrates, could create beings that exist as pure information. Such digital minds might be transmitted across interstellar distances at light speed, arriving at distant stars in years rather than decades. Upon arrival, digital minds might be instantiated in robotic bodies or in biological forms grown from stored genetic material. The beings that walked on planets orbiting Alpha Centauri might be human in origin, but utterly different in physical form from the biological creatures that first dreamed of reaching the stars. Mind uploading assumes consciousness can be faithfully reproduced in digital form, an assumption that remains philosophically contested and scientifically undemonstrated. The nature of consciousness remains one of the deepest unsolved problems in science. Whether subjective experience can exist in computational substrates, whether a digital copy would truly be the same person as the biological original, whether uploaded minds would have moral status equivalent to biological humans, these questions have no agreed answers. Even if such technologies prove possible, the beings that reach distant stars through such means would be unrecognizable as human by current definitions. They would have no biological bodies, no evolutionary heritage, no connection to the physical forms that shaped human culture and psychology over millions of years. The harsh reality confronts us with uncomfortable truths about our cosmic situation that no amount of technological optimism can dissolve. We evolved on a small planet, orbiting an average star in an unremarkable region of an ordinary galaxy. Our bodies and minds are exquisitely adapted for conditions found on Earth's surface and nowhere else in the known universe. The cosmos beyond our tiny oasis is hostile beyond anything our ancestors imagined when they first looked up at the stars and wondered. The radiation would destroy us. The distances would isolate us beyond psychological endurance. The timescales exceed human generational continuity. The engineering requirements surpass our manufacturing capabilities by orders of magnitude. Jupiter, visible in the night sky as a bright wandering star, lies beyond practical human reach with any technology we can currently envision or reasonably project into the foreseeable future. The challenges of radiation, propulsion, and mission duration compound into barriers that no combination of engineering solutions can overcome within timescales relevant to anyone alive today. Alpha Centauri, the nearest star system. The 4-light-year gap represents a distance so vast that crossing it would require either technologies that violate known physics or timescales that exceed human civilization's demonstrated ability to maintain coherent purpose. This confinement need not be permanent in an absolute sense. Technologies that seem impossible today might become practical over centuries or millennia of continued development. Human ingenuity has overcome challenges that once seemed insurmountable. Our descendants, if humanity survives long enough, might develop capabilities we cannot currently imagine. But for us, for everyone alive today, and likely for many generations to come, the stars will remain unreachable lights in the darkness. We can study them with telescopes. We can send tiny robotic probes that may never return useful data. We can dream of worlds we will never visit and write stories about voyages we will never make. Perhaps this limitation is not entirely bleak. The universe's vastness ensures that any threats too distant to reach us cannot affect our world. We are protected by the same cosmic gulfs that imprison us. Whatever dangers might lurk among the stars, they cannot cross the void any more easily than we can, and perhaps the knowledge of our cosmic imprisonment should inspire us to cherish the one world we can inhabit. Earth is not merely our home, but our only possible home for the foreseeable future. If we destroy its habitability through war, environmental destruction, or simple negligence, we have nowhere else to go. The stars will wait. They have burned for billions of years and will continue for billions more. If humanity survives its current challenges, if our descendants endure long enough, if technologies advance far beyond current imagination, someone bearing our heritage might eventually reach beyond the solar system. But that achievement, if it ever comes, lies so far in the future that it might as well be never for anyone alive today. The honest truth is simple and stark. We cannot reach Jupiter in any meaningful sense with current or foreseeable technology. Alpha Centauri is beyond impossible. The cosmic cage is real, and we are trapped within it. Yet perhaps being trapped together on this remarkable planet is not the worst fate imaginable. Perhaps learning to share our single world peacefully is the challenge we were meant to face, not racing towards stars we cannot reach. The universe is vast beyond comprehension. The stars are beautiful beyond description. And we are here, together, on this small blue world, gazing up at lights we may never touch. That is the harsh reality. That is where we find ourselves. And perhaps, if we learn to appreciate what we have, rather than mourning what we cannot reach, that is enough.